Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about how we can implement B plus tree as an index file in the DBMS. First we will discuss about the structures of an B plus tree and how can we query on an B plus tree index files. As we know that the sequential ordering, even with the clustering and non-clustering, provides a large overhead of the computation time, the memory, and also the access time. So we need some more enhanced features on index files that we can use it so smoothly that the fetching of data becomes easier to us. So we use one other type of index files that is known as a B plus tree index files. The B plus tree index files is nothing other than the concept of the data structure B plus tree implied on an indexing on the data. That means now not only a multi-level of ordering, we will enhance the multi-level indexing by one more point that even if on a non-candidate key or a candidate key, we can move directly by storing the pointer to it and we can fetch the data by pointing directly to the result, not by a sequential ordering. That means even when the clustering and non-clustering both were used for indexing, we know that there is a sequential storing for that. That means one tuple followed by another one, followed by another one, and the last tuple will points to null. But with B plus tree index files for a given table, we can use just by pointing to the data using a tree-like structure. B plus tree is a balanced tree where it starts with a root node. Now the root node in every node of this B plus tree has got a pointer field associated with it. So the root node has got a pointer to it. Now if we define the level of the tree, that is n, that means there will be n number of pointers associated with each leaf node inside that tree. And there is a balanced tree, that means for a level to children live or node to the path, there will be a fixed number of paths or levels are there. Say for example, if there are n numbers of pointers, there can be from n by 2 to n fixed routes for having access to the leaf nodes. So we can have that for n equals to 4 pointers attached to each of the leaves. Now, how can we store the data in a B plus tree? So we can know that when we are pointing to the left one, it is of n equals to 1. So we may want to add another up pointer to it. So the first one refers to the left and the next one refers to the right. So every value, that means that the value part of an index should be lesser than the left one and greater than the right one. That means the left one will got a lower value and the right one will get an higher value to it. Now, if it is a value, then L is denoting the lower value and H is denoting the higher value. Now, what happens if we are not following a numerical order? So if it is an alphabetical basis, then we will choose the same way, like A is preceding or lower than B and C is highestly succeeding or greater than B. So we will form our B plus tree as an indexed files on DBMS. To start with B plus tree, as we know it is a balanced tree and has got an n by 2 to n fixed path of accessing. So if these are the leaf nodes or the children of the root tree, then it must be exact same number of way to reach the L and to the H if they are the siblings of the tree. So in this way we can store the data. Now let us look at a formal relational structure on a B plus tree. Now if P1 to Pn are the values that is stored in an index key, that means they are the values, and there are K1 to Kn that are the search keys on an index tree. Then the B plus tree on a simple basis looks like this with n equals to 1 pointers. So in this way, P1 starting from associated with the search key, P2, then Pn minus 1 for Kn minus 1 and Pn to Kn. So in this way, we can just adjust our B plus tree on indexing. Now let us build the table or a relation instructor on which we will form a different level of B plus tree and see how we can modify our indexing to that. Now first let us create a leaf node indexes on this one. Leaf node indexes means that will go directly to the values. No other ordering or treeing indexes on this one is not necessary. So first we are just using the indexes that will point directly to the values. Then we will add up to the hierarchical tree to this leaf nodes. We will take only a number of examples, not all of this. Now here the leaf nodes that has got the leaf values. That means the values that will point directly to the instructor relation. So now Woo pointer will point to Woo. Creek will point to the creek. And finally cats will point to the cats one. So there can be also a number of leaves that is attached to this one that we can add it on this way. So now the problem with this problem that Woo, creek and cats cannot belong to an n equals to 3 B plus 3 indexing, because if n equals to 3 then the child root can have 3 pointers at max. Now the values that is W, C and K cannot belong with each other, because we know that there will be ordering to that particular value. So if it is I less than J, then we must suggest that Ki is less than Kj. That means the search key to the I is less than search key to the Kj. So W is not less than C, that cannot hence move further that left of the C. So if it is I and J, so it is ordered that I greater than J or Ki greater than Kj. Now let us create a multi-level or non-index and non-leaf indexes on that particular B plus tree. So now we will consider a proper ordering that all the alphabetically lesser value will be in the left one and the higher value will be in the right one. So how to insert that when we are actually inserting a value to the particular leaf, or we can go a lower level of ordering. Let us just first create the B plus tree. Now say for we can look for these conditions. Say if there are m pointers, that is I equals to 1 to 2 to m, and if we are talking about a pi on that value, that will search to the k of this 1 to m type of these pointers. So always pi should be lesser than, that is ki is lesser than ki minus 1, so that we can, following the rule, insert the values in the p plus tree. Now if we are talking about the last pointer in a leaf node pm, then of the subpart or a part of the leaf node, then it can point to the maximum of km minus 1, not more than that. That pm cannot point to km, but it can point to km minus 1 at most. So if there is any km field that is we want to add to the B plus tree, we have to make it another subpart or a leaf node to it. Now we will create a non-leaf index on this B plus tree. In this creation, as our name is the key here, that means on name we are creating the index, I am inserting only the names, not the whole relation on the instructor. So for our designing purposes, I am taking only the name field on the instructor relation. So my B plus tree will be of order n equals to 4. So the root node, first it will got the kim value. Now I am here showing only the final one, which is got this root node in this way, that the left part will be the lesser than and the right part will be the higher than. See, as n equals to 4, so we have 4 pointers, but all the pointers will be null because only creek is the root node. So this we can define as the root node. Now as we know that if C is the root node, then K and W both will be considered as the right part. So now I am taking that creek is not the root node because K and W both will come in the right side. So we need to balance the tree so that every leaf node will have the exact same number of levels. Let us consider Kim as the root node. So now we can see that Kim's left part has got K, 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 K and also C because all are lesser than K. And W has got in the right part. So how can we adjust that is in the Kim one. So if I want to, then the Kurt, Katrina, Karin and Cats and Creek all will be in the left part and only Wu will be in the right part. So again, this will also make it unbalanced because we cannot adjust Kurt, Katrina, Karin, Creek and Cats in a single leaf node as Wu will be the single leaf node in the right one. So again, we need to make some ordering to this. Now let us start with this one, cats. Now with the cats, we have on the left tree, we have this Katrina, Kurt, Creek, because all belongs to K and A and T. See, K, A, T is the first one for these two matches, but as R is lesser than, because R is lesser than T in alphabetical order, so we can take this one as the lesser one. So we are here taking that cats as the root node. Now see, we can create an index tree on a B plus balanced one. So the left one will have an, so we have two leaf nodes now. Now see, we can accommodate in these leaf nodes all the values or not. So belonging to cats, we have the light one as Wu, Kim, and Karin. That all are greater than cats. So we can accommodate this tree here. But let us see that we accommodate this cards, Katrina and Cream in this way that we can accommodate in this one. Now see if we can accommodate all this Kim, Vo and this Creek and the card Katrina on the second one. So the cats and the left of the cats, what we have? We have cards, we have Katrina and we have Creek. So we can accommodate like Kurt, Katrina and Creek. But in the right one, we have Kim, Wu, Cats and Kerry. So we cannot have inside this tree. So now we need to make an internal leaf so that I can have on this cats and on the left one to it. So on the cats and on the left one of cats, we can have this Kurt, Katrina and Creek. So I will choose that between this Kurt and Katrina on the Katrina. Because on the left of Katrina, we can have the Kurt and Creek. But see, if we make Kurt and Creek here, there will no one for the right one and Katrina. So now we cannot make Katrina here. We need to make another index tree with the cats on the root node and not the Katrina, but the Kurt on the right left node. Now on the left two cats, we can have the Kurt. Now on the right to Kurt, we can have the Kurt and Katrina, and on the left, we can have the Creek as the leaf nodes. Now on the right to Kurt, we can have Katrina and Kurt. Now see, even we have called the values on this one, we should got every value in the leaf node. So it is not one that if we have the leaf node and this internal node where we are using, we should have the values on the right children node and the left children node too, so that we can point to the direct values. Now let us go to the right side of cats that has got the Karin, Wu and Kim. So for Karin, Wu and Kim also, if we to maintain the balanced one, we need to put the Kim in the middle so that we can have the Karin on the left child and the Wu and the Kim as the right one. Now see, if we got this all leaf nodes, they are all in the same level, then this is the root node. These are some internal nodes and these are some leaf nodes. So from this one to this one, we have this 2, this one to this one degree 2, also this one 2 and this one also 2. So it is always better to draw this that we can have on the same line so that we can easily say that they are on the same degree. Now there is a linking from this one on the leaf node, just like this one, so that we can say that every link node is connected. Now this creek will now point to the value creek in our table. The Karth will the Karth, the Katrina to the Katrina, Karen, Kim, Wu, all to the actual values that we presented in our table relation. So in this way, we can create an n equals to 4 of b plus 3 index on this one. Now what will happen if I want to create an b plus index 3, that is n equals to 6 on this one. Now let us create an b plus 3 index so that we can reach an n equals to 6 on this one. Now we have 6 pointers at most in every leaf node or in the root node or internal node. Now see, if we increase the number of pointers in an b plus 3 index files, then obviously the number of degrees or the number of levels will be lower. So in this n equals to 6, it is possible to have that we are only having 2 leaf nodes and 1 root node for our index files instructors. Now I will start with an n equals to 4 that I have started with, that is Kim as the root node. Now let us see what happens if I want to put that, and can I get only 1 root node and 2 leaf nodes out of this one. So now my left tree will have, so first it will have creek, next it will have Kurt, next it will have Katrina, and finally it will have cats. Now see that we have Karen 2 that we need to include in our Kim root node. And we have 1, 2, 3, 4 and 1 pointer and the data value left. So now we can accommodate all the 5 childs to the leaf node, Creek, Kurt, Catherine, Cats and Karen. And from this Kim, we can have the Wu as its right node. So now we can accommodate all this one with these 3 nodes instead of having 1, 2, 3, 4, 5, 6, 7 nodes. So see, if we increase the number of pointers in a node, then we can have a lesser degree or lesser number of nodes. So now everyone will point to their values in the field. So what happens there? Now we can see that if I want to go to Katrina, we just don't need to see all the values till the Katrina. If the Katrina is the last one too, then we do not have to just check for log B2. That means if there are B numbers, then log B by 2 number of preferences for searching Katrina. We just need to find the pointer to Katrina and then we can have the value to Katrina, because the values are even not stored sequentially. They are just stored in an exact fashion that the values are coming to the instructor relation. And with this B plus 3 index files, we can move to every type of possible references without just sequentially accessing them. Now let us look at this one, that how can we query on a structure that we have formed on an B plus 3. Say for an example that we want to find a search key on value V on a structured tree on the B plus 3. So now we will write the query in SQL to find function using the value V and then find the actual value of V corresponding to which index and it is pointing to. So we are using the function find to with the use keyword function, then the function name and the argument that is value V which you're finding, and then we will introduce a search key that is ki. Now it will return a leaf node C with an index I in such a way that pi points to the index C on that leaf node. Now first we are starting with making C equals to the root node. Now we will perform looping it until and unless we find C in the leaf node. Because we have started with C the root node, just like our previous example that we have started with cats, Kim, and we need to find each of them in the leaf node so that we can directly point to the value associated with this ordering in the B plus 3. Now if ki is the search key, then we need to find the smallest number I. That means the smallest one. Like we are finding that Kurth is the first one to be put in the B plus 3. So we are finding in such a way that as our value is less than the search key that we are finding, so that we can have the value as the left leaf node. If we cannot find any I that is less than the V, that means we cannot find any search key or the value against we are searching, that this is the least value that we can have in the index. So we have reached the index 1 with the value that is the least value that it can store. Now we are considering PM as the last non-null pointer. That means that is the M pointer. We can say that it is pointing to M minus 1 node. We have already discussed in the structures of this B plus tree that if we are pointing to the M node, that means we can have M minus 1 pointer at most. So PM just belonging to the last non-null pointer, because the last pointer will obviously points to null. Now we are pairing up our C, which is the root node till now, and with this pointing P1. That means now my C value will point to the exact number of root node that we have make it to the leaf node, because it is containing the least value that we can have against any Ki. Now what happens if value is equals to the Ki? That means we have not reached the least value as V, but the least value as Ki, and both Ki and V has got the same value. Then we need to perform the same with the Ki. Now the Pi, that means the pointer to the search key Ki, I am attaching C with it, because the PM is not the non-null pointer, but the Pi is now, because V and Ck has got the same value. Now that we get after this one, because I is the smallest number, we cannot find such I other than the V. That means V is belonging to C, which is now become my leaf node. So the root node has now become my leaf node, that we have moved through this either PM or Ki. That means if it is not PM, that means it is pointing to some other node, and if it is the exact node that we are finding, then V is attaching with the CKi. Now I be the value where Ki equals to V that we know. Now we will return the C based on this value V. Now that we have reached the C and I, because C is the node that is containing the value V and search key Ki, so that if there is such I, we will return Ci. Otherwise we will return null, because we could not find any of the Ki that has got the value V. Now this is of querying and pointing a particular search value. Now how to print this value to our result? Now that we can see that print all is a procedure that doesn't got any return value, because it will traverse all the values until and unless the matching value is found. That means we have found the index. Now we want to print that index so that we can have the value reported by our query. So now we have said done, the variable equals to false, because when it will be true, our task will be over. So this one will print all the values that matches with the search key with the value V. So now we are taking that Li is a combination of a search key and the index I, so that it matches the value with V. Now if there is no such pair, that means if the value is null, that means it has returned null from this one. So we will just return from the function without printing any of the documents. Now that if we have this Li not equals to null, then we will repeat the repeat. That means the first repeat is for the outer one, and the next repeat is got the every attribute of this value. So we will first find the record and print it, which is got referenced by the Pi and has got the L within it. Now we will move to our next type. So we will repeat this until and unless we found something that is greater than V. That means we have reached and traversed all the left leaf nodes, and now we have finished with the left leaf nodes, and we will move to the next parent node so that we can go to the right leaf node. And until and unless I is greater than the number of keys in L. That means if the number of keys in L is 4 and I is 5, that means 4 we will move, and the next one is for moving the part to the right node. Now even if after that we have suggested the number of keys in L and we have already traversed the loop in this, and if we get out from this loop and see that if still I is the number of keys in L, that means I has got some greater values that the number of keys in L has got. That means now my L belongs to the Pn, that means pointing to the N. That means we have already performed all this one, and now we will see this one as a next and right leaf node. Otherwise, we will set done equals to true, because we have done for this left and right leaf nodes. All the nodes in this one has not been traversed. So this is for printing all the records that belongs to a particular value v, and we can have all the records matched with this. Now when we talk about a value v, it could have been belonging to the root node. Now the root node has got the pointers left one and right one. Again that can has the pointers left one and right one. So in this way we will have all the values that belong to the root node, not only the adjacent values of the leaf node. Now let us see this example more elaboratively. Now see this one examples that if we have to find some salaries that ranges between 50,000 to 1 lakh. That means we need to find all the information based on the salary. So we can have the range as a search key, not a particular value. So the L comma U is my pattern now that we have no for the B plus tree, and any for the indexing we can have a combination of key in this way that if L is U and a pattern to this, then a combination Li is greater than Ui. So we should follow these rules to the we can have L comma I as an index key pattern. So first it will search for this L. For now it is 50,000 and for U it is 1 lakh. So we have this 50,000 and 1 lakh as our range, and it satisfies that 50,000 is less than 1 lakh. So how can we do that? We can create a sparse index in an ordered one, but as we are talking about an B plus tree and the implementation just we have followed, so we can implement it that the L comma Pn, that the L dot Pn combination will be higher for this 1 lakh because all the value associated with 1 lakh now will be put to in another one, and the 50,000 will be in another one. So now my B plus tree will be made on a salary, not just the particular value of a name. So when we are salary making on a B plus tree, then we need to include if there is one salary for more than one person. It can happen. So now 60,000, 70,000 and all will come to the value on the range. So the every leaf node that we are traversing within this range. So now we will take the value of the leaf node and add one more condition here that if Li is less than V. So if this condition is added to this one, then we can easily fetch out that we can take all the ranges and the repeat loop will be repeated until and unless we can find the left one, because 50,000 to 1 lakh we can take it as the left node. So it is only in the lesser than relation or in the greater than relation that we can take that 50,000 as the root node and the 10 lakh 2 in the writer one. We can have another internal node and writer one, it doesn't matter. Just put the value L and U as a range to the query and make this update Li is less than V, so that we can have all the values is lesser than or V is greater than Li, so that we can have all the values in the right node. So in this way we can use this querying of data to get input this B plus tree, and if there is n equals to 100, that means for larger database, that is the more use of an B plus tree, that we can use a more number of pointers to the database, so that we can have the smoothly having log n by 2 reduction of number of searches, so that we can have to search in 1 million entries. So in this way we can just halve the searches by increasing the number of pointers in a particular node. So that is all for the structure of a B plus tree and querying on B plus tree. Later on next videos we will discuss about updates on B plus tree and the complexities on the B plus tree. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.